Hi, this is another video in my series on the special theory of relativity, and specifically how to derive the Lorentz transfer or the Lorentz factor. It is related to my other videos, my video about Einstein's clock and how that is wrong, and my other video about the speed of light, the basic assumption that the speed of light is constant. So this video is another way in which we can derive, supposedly anyway, derive the Lorentz factor purely algebraically. But it also depends on this assumption that the speed of light is constant. So once again, it's wrong. The derivation is wrong. But we'll see how it goes. Imagine a stationary object with a stationary observer who has a clock and he can measure time, which we will call t. He can also measure a certain distance, which we will call x. Imagine also a moving object, a moving observer, who can also measure time, which we will call t prime from his point of view. The object moves in that direction with velocity v. He can also measure a distance which we will call x prime. The distance moved by the object is given by v multiplied by t or t prime depending on the frame of reference. Imagine now also that there is a flash of light in the distance. The stationary observer will measure the speed of light to be x over t, and the moving observer will also measure the speed of light to be x prime over t prime. Now it seems pretty obvious from this that the distance x equals x prime plus vt prime, and the distance x prime equals x minus vt. This is our starting point. So we have a stationary observer and we have a moving observer, and we have our two formula for distance. X equals x prime plus vt prime and x prime equals x minus vt, and we have our two measurements of the speed of light from the two different points of view. From that we can see that x equals ct and x prime equals ct prime, so we can substitute in our distance formula and we get ct prime equals ct minus vt, and ct equals ct prime plus vt prime. Now the crucial point is t and t prime the same? In classical physics it would be the same. The two observers measure time the same way. So if that is the case, then t prime and t will cancel throughout these formulae, and we end up with c equals c minus v, or c equals c plus v, which means that the speed of light is less than itself or greater than itself, and that cannot be. So we have a problem here once again, starting with some basic assumptions about classical physics, that the speed of light is constant, and also that surely time is measured in the same way, whether you're moving, whether you're stationary. Things like distances, they would seem to be the same whether you're moving, whether you're stationary. But we've reached this absurd conclusion. We've reached the conclusion that the speed of light, c, is less than itself in one frame of reference or greater than itself in another frame of reference, which is absurd. This is a reductio ad absurdum of something. So the way that we would normally proceed here is to try and find the error. We need to try and find the error factor. And so that's what we'll do now. We will now try to find the error factor, which we will call gamma. And the way we do this is a tried and tested mathematical device where we add the error factor to our formulae. We then multiply the formulae together. Again, a well-established mathematical device. We will then solve this equation for gamma, and we will find out, as we have before, that gamma equals 1 over the square root of 1 minus v squared over c squared. That is the error factor. Now that we have the error factor, or the Lorentz factor, we can see that relative time equals proper time, the time when the object is not moving, multiplied by gamma, which means that relative time equals proper time divided by the square root of 1 minus v squared over c squared, which is known as time dilation. Relativistic length is slightly different. It is equal to proper length, that's the length when the object isn't moving, multiplied by 1 over gamma, which means relative length is proper length multiplied by the square root of 1 minus v squared over c squared. And this is what we call length contraction. Most importantly, relativistic mass is equal to proper mass multiplied by gamma, which means relativistic mass equals proper mass divided by the square root of 1 minus v squared over c squared, from which we can derive the famous E equals mc squared, or that's one of the ways in which we can derive that formula. We can also derive the relativistic velocity formula using the error factor gamma. We start with the distance formula, which includes the error factor. We can say that c is x prime over t prime, which means t prime is x prime over c. We substitute for t prime and we get this. Then we divide throughout by c and we end up with a relativistic formula for time. So we have the relativistic distance formula, the relativistic time formula. Velocity is still distance divided by time. The gammas will cancel and we have a relative velocity formula. Now this easily transforms into our familiar by now u plus v divided by 1 plus uv over c squared. So as I said earlier, this video is related to my other video about Einstein's clock, except this one doesn't use a clock or a thought experiment. This is purely done algebraically. Now I haven't shown all the algebra because the algebra is not that important. There's nothing wrong with the algebra. If you want to see the complete algebra, then here it is now, and you can pause the video and study the entire algebra. But it's not necessary. It's not the algebra that's the problem. Once again, the problem is the basic assumption. The basic assumption that the speed of light is constant. Without that, none of this works. And that's the thing that we have to challenge. Because as we've seen before, the speed of light is not constant, not in the way that Einstein thought. And so once again, the derivation of the Lorentz transform has failed.